Hi, today's lesson is going to be lesson 2.2. We are going to be working with scientific notation and positive powers of 10. So let's get started. I'll share my screen with you. Hope you're having a great day today. Put that away and press present. So here's our lesson 2.2, positive powers of 10 with scientific notation. So at the end of this lesson, you will be able to say, I can write a number in scientific notation, and I can write a number in standard notation. We'll be working from standard 7EE3, use numbers expressed in the form of a single digit times an integer power of 10 to estimate very large or very small quantities, and to express how many times as much one is than the other. So today we're going to be talking about the very large numbers, and in our next lesson we will be talking about the very small numbers. So I'm going to minimize myself as we get started. And let's go here. Okay, here's my math meme of the day. So the cat's saying, I thought I didn't understand math until I learned scientific notation. And then we have a girl, and she's a middle school girl, saying, scientific notation is easy. And hopefully that will be what you're saying at the end of this lesson. What does the cat say back? He says, ish. Okay, let's see how we do. Definition, what is scientific notation? Well, scientific notation is a method of expressing very large and very small numbers. Today we're focusing on the very large numbers as a product, that means multiplied by, as the product of a number greater than or equal to 1 and less than 10 and a power of 10. So when we show this in numbers, it makes more sense. Here, for example, is 250,000. Written into scientific notation as 2.5 times 10 to the 5th power. So what is 10 to the 5th power over here? What is 10 to the 5th? Well, that's 10 times 10. Keep going. How many tens? Right, a total of 5 tens. It's 10 times 10 times 10 times 10 times 10. By now, you're pretty comfortable working with exponents and bases. So 5 tens. So what is 10 times 10 times 10 times 10 times 10? That equals, did you say 100,000? If you did, you are correct. 100,000. Notice that there are 5 tens and 100,000 has 5 zeros in it. Okay, and then you multiply it by 2.5. So 100,000 times 2.5 is equal to 250,000. So scientific notation is just another way of writing very large numbers. You could argue that 250,000 isn't really a super huge number, but when you become a scientist, or if you become a scientist that, say, studies the galaxies, you are going to want to write your super huge numbers, which have tons of zeros after them, in scientific notation, a shorter way. You wouldn't want to have to write all those zeros after a number that's very, very large. If you are somebody that studies microorganisms, you again would want to write a number that doesn't have 0.000000000 a million times and then the number, right? So you're going to want to use scientific notation. So that's what it's used for. So let's go on and see how to write in scientific notation. So writing a number in scientific notation, let's start with 93 million. Now that's a pretty big number that we probably want to start using scientific notation for because of all the zeros that we're dealing with. So step 1 is to move the decimal point until you make a number between 1 and up to 9.9. You don't want to get to 10, that would be wrong. So here's our number. So first we're going to put our decimal point after the number because it is assumed that there is a decimal point after the end of every number. It's just we don't show it if there's nothing to the right of that decimal place. So we stuck our decimal in there at the end. Now we are going to move until we get a number between 1 and 9.9. So we moved one place, we moved another place with our decimal. We're moving a third jump with our decimal. There's a fourth jump, a fifth jump, a sixth jump, and finally a seventh jump. So now we have the number 9.3. And 9.3 is between 1 and 9.9. So 9.3 works. That's our first step. Step 2 is to count your decimal jumps. Well, how many decimal jumps did we do? We did 1, 2, 3, 4, 5, 6, 7, right? We went 7 jumps to the left. So that's going to become our power of 10. So step 3 is write your new number times the power of 10 that equals how many jumps you made with your decimal point. So our final answer would be 9.3 times 10 to the 7th power. If I were to take 10 to the 7th power and multiply that by 9.3, I would get 93 million. So it's just another way of writing 93 million. Let's see another one done for us. Okay, this time we're going to write 570 trillion in scientific notation. Or is that billions? One's tens, 100,000, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions. 570 billion, not even trillions. So 570 billion. Okay, step 1, move the decimal point until you make a number between 1 up to 9.9. There's our number. We're going to assume the decimal is at the end of the number, and we're going to just start our jumping. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 5.7 is between 1 and 9.9, so that is where we will stop. And 5.7 will be the number we use. Step 2, we're going to count how many decimal jumps we've made. So we just counted them. Let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So we have gone 11 jumps left. And by the way, don't start counting until you've actually jumped. So if you start here and you say 1 and then you jump and say 2, you're going to be off, right? You start here and you jump and then you say 1, and then you jump and then you say 2, okay? So you don't get messed up when you get some really large numbers. Step 3 is to write your new number, 5.7, times the power of 10 that equals how many jumps you made with your decimal point. Well, we made 11 jumps, so our final answer is 5.7 times 10 to the 11th power. All right, and if you wanted to try that on a calculator, you would see that if you did 10 to the 11th power and you times that by 5.7, you would get 570 billion. Okay, let's give you a chance to try this, and I will see you back in a moment. Welcome back. Let's move on. We have another definition. We have to talk about standard notation. Our last one was about scientific notation. This definition is about standard notation. Standard notation is just the normal way of writing numbers. It's the way you've always written numbers. So for example, 7.8 times 10 to the 4th power can be written in standard notation as 78,000. So that's the normal way you would see the number. So how do we do this? We're going to write 3.5 times 10 to the 6th power in standard notation. Step 1, we're going to move the decimal point the number of places shown in the exponent of power of 10. This time we're going to move our decimal to the right instead of to the left because we are going to take it out of standard notation. So we're going to do the opposite of what we did to put it into scientific notation. So we're taking it out of scientific notation. So we have 3.5. There's our decimal, made it nice and big for us to see it. We have to move 6 spots to the right. Number's got to get bigger. There's our 6. So we're going to move it 6 to the right. Here we go. 1 spot to the right, 2, 3, 4, 5, 6 spots to the right, and our decimal is now over there. But what do we do with all those jumps that are empty? Well, step 2 is to fill in your empty jumps with zeros. Here's a 0, there's a 0, there's a 0, there's a 0, and there's a 0. And our final step then is to add commas after every grouping of 3 numbers, and you're done. Remember, we add commas from the right, not from the left. So here's our number. Let's put our commas in. So we go 1, 2, 3, and I got to move my arrow here. It puts that black bar at the bottom, and then we put another comma, 1, 2, 3. So we have 3,500,000. So that's what 3.5 times 10 to the 6th equals. Let's try another one. We're going to write 7.034 times 10 to the 9th in standard notation. Number 1, move the decimal point the number of places shown in the exponent of the power of 10. Well, there's our number. There's our decimal place. How many spots are we going to move it to the right? 9, because our exponent is a 9. So move 9 to the right. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Be very careful on your jumps and your counting and your lines, right? Be very neat and organized with this so that you don't get off on missing a jump. So now we do what? We fill in our, first we're going to move our decimal. Then we fill in our empty jumps with zeros. There's a 0, there's a 0, there's a 0, there's a 0. Where did it go? There it is. There's a 0, and there's a 0. What's our final step? Add commas after every grouping of 3 numbers, and you're done. There's our number. So going from the right, every 3 numbers, we put a comma, another comma, and we have another grouping of 3, so we put another comma. That is, let's see, 7,034,000,000. 7,034,000,000. Okay, now you're going to get a chance to give it a try. See you back in a minute. Okay, welcome back. Hopefully you did well on that. We're writing from scientific notation to standard notation. Let's move on. Scientific notation in real life. Yes, it has a use. It is useful. A single little brown bat can eat up to 1,000 mosquitoes in a single hour. 1 hour, it eats 1,000 mosquitoes. That's a good thing. It's good to have bats. Express in scientific notation how many mosquitoes a little brown bat might eat in 10.5 hours. Well, he eats 1,000 in 1 hour. 10.5 hours, how many is he going to eat? Well, we have to multiply. So step 1 is to multiply our 1,000 mosquitoes in 1 hour times 10.5 hours. If we do that, we get 10,500 mosquitoes in 10.5 hours. Now we want to write that in scientific notation because the problem tells us to express it in scientific notation. So we write this in scientific notation. How would we write 10,500 in scientific notation? We start our decimal at the end. We jump until we get a number between 1 and 9.9. So we go 1 jump, 2 jumps, 3 jumps. Am I there yet? No, because 10 is too high. And 4 jumps. So now I have 1 point, put our decimal there now, and erase the decimal here. And I now have 10.500, or just 10.5, correct? So, and how many jumps did we make? 1, 2, 3, 4. So it'll be 1.05 times 10 to the 4th power, correct? Yeah, 1.05 times 10 to the 4th power. Okay, let's take a look at another example. In real life, a tropical species of mite named, and I don't know if I'm going to say this name correctly, if when you were in 7th grade, you might have thought of all those long names we had for animal species. Archicozetes logistosus. So that mite is the record holder for the strongest insect in the world. It can lift up to 1.182 times 10 to the third times its own weight. That's a huge amount. If a 120-pound middle schooler was as strong as this insect, how many pounds could that middle schooler lift? So we want to see just how strong is that insect compared to what a middle schooler would be if it could lift that much, right? So step one is to write 1.182 times 10 to the third in standard notation. How do we do that? Well, we have to get it off of scientific notation by moving our decimal 1, 2, 3 places to the right, because we have a little 3 here, right? So that would end up being 1,182. So that's how many times its own weight this little insect can lift. So now we're going to think about that in terms of a 120-pound middle schooler. Okay, so if a 120-pound middle schooler could lift 1,182 times its weight, what would that be? So we're going to multiply our number by the middle schooler's weight. 1,182 times 120 is equal to 141,840 pounds. So if you were as strong as that bug, that mite, you would be able to lift 141,840 pounds. That would be crazy. So that's a pretty strong bug, wouldn't you say? Yes. Okay, moving on. Think about this. Which of the following numbers are written in scientific notation? 0.641 times 10 to the third. No, that number needs to be between 1 and 9. So 0.6 is before 1, right? 0.6 over here is too small. It has to be between the 1, actually between 1 and 9.9. I should say 9.9. Okay, let's look at the next one. 2 times 10 to the first, is that written in scientific notation? Well, you have a 2, that's between 1 and 9.9, and you have a 10 to the first. Can you have a 10 to the first? Yeah, of course you can. That's just 10, right? 10 to the first power is just 10. Yes, because the number is between 1 and 9.9, and 10 to the first is a legitimate power of 10, right? That's just 2 times 10. That's just 20, because 10 to the first power is 10, and so 2 times 10 is 20. That's just another way of writing 20. Next number, 4.38 times 5 to the 10th power. Is that written in scientific notation? No, why not? Because 5 is not correct. It has to be a base of 10, right? 5 to the 10th is not a power of 10, it's a power of 5, right? So the base has to be 10, not 5. And the last one, 9.999 times 10 to the fourth. Is that written in scientific notation? Yes, of course, that's below 10, right? First number is between 1 and, well, it's 9.999. It's lower than 10, right? And the second number, 10 to the fourth, is a power of 10. So that one is also written in scientific notation. Okay, another think about it. Which measurement would be least likely to be written in scientific notation? Least likely. Least likely. Number of stars in the galaxy. Number of grains of sand on a beach. Speed of a car. Or population of a country. Remember, scientific notation is used for very large and in the next lesson, very small numbers. So which ones can we eliminate? We want to pick the one that probably will not be written in scientific notation. Well, let's get rid of number of grains of sand on the beach, because that's going to be a huge number, wouldn't you say? Exactly. What else can we get rid of? Right, number of stars in the galaxy is also a very huge number. And the last one that you can get rid of, population of a country is a very huge number. So the speed of the car is least likely to be written in scientific notation. All right, you get a turn at these types of problems. Welcome back. Hopefully you did well. Let's talk about a little higher order thinking. Figure out which number is greater without writing them in standard notation. Without writing them in standard notation. 4.5 times 10 to the 6th or 2.1 times 10 to the 8th. Which one is bigger? Well, there you go. Did you say 2.1 times 10 to the 8th? Well, why did you say that? Why is it bigger? How did you figure it out without putting it into standard notation? Well, you look at the exponents, right? You look at the little 6 and the little 8. Well, the 8 is bigger than the 6, so 10 to the 8th has 2 more zeros than 10 to the 6, so it is much larger. So that's how you look at it and compare. Clear my drawings. Okay, you get to try one, comparing some numbers in scientific notation. All right, welcome back. This is the end of our lesson. Your homework for lesson 2.2 will be on Google Classroom, and I will see you next time. Have a good rest of your day. Bye.